Run and get a glass of water and put it on the table next to you. Take a good long look at the water. Now can you guess how old it is? The water in your glass may have fallen from the sky as rain just last week, but the water itself has been around pretty much as long as the Earth has. Earth has been recycling its water supply for approximately 4 billion years, ever since the outgassing of water vapor, and its cooling to form liquid water. Many scientists believe that most of the Earth's water supply was created when the Earth formed, and that large amounts have not been gained or lost since. The oceans contain most of the water, while the majority of the water people can drink, fresh water, is in glacier ice and floating on ocean tops in cold regions. One model to illustrate the movement and the phase changes of water at and near Earth's surface is the water cycle, also called the hydraulic cycle. The water cycle is fueled by solar energy, insolation, which changes liquid or solid water to water vapor, and by gravity pulling water down in the atmosphere, hydrosphere, and upper parts of the lithosphere. The ultimate source of most water on land is the evaporation of the ocean's water. The moisture gets to the land from the oceans by way of the atmosphere. When precipitation falls on the land, 4 things can happen to it. Precipitation can be stored or retained on the land surface as ice or snow. Water retention. Water can also be retained on the leaves of trees and other plants. I'm sure you've seen this water retention before. Precipitation can infiltrate or seep into the upper parts of the Earth's lithosphere under the influence of gravity. Think of seeping like water into a sponge. The sponge soaks up all the water. All of the Earth's water beneath the Earth's surface is called the subsurface water. Which we write down here, this would be the subsurface water. Precipitation can flow over Earth's surface as runoff. About 1/3 of precipitation falling on land is returned to the water cycle through runoff. So right here we have the runoff going back down into a stream, and then this would become recycled. Another example of runoff off of, say, a mountain down into a lake. The combination of evaporation and transpiration is evapotranspiration. Evaporation out of, think of a hot cup of tea, the water evaporates out. Transpiration is what the plants and trees give off. It usually includes the sublimation of ice and snow directly into water vapor. Approximately 2/3 of precipitation that falls on land is evaporated or transpired back into the atmosphere somehow. Many factors affect infiltration. Most infiltration occurs in a loose material, including soil, that directly covers much of the Earth's solid surface or is beneath a thin vegetation zone. Some infiltration can also occur into rock exposed at or near Earth's solid surface. The amount of water that can infiltrate when precipitation occurs depends on several variables. One variable is the slope of the land. The steeper the slope or gradient of Earth's solid surface, the less infiltration or seepage we have. Another factor is the degree of saturation. The more saturated the loose materials at Earth's surface, the less infiltration. This figure shows that the Earth's surface is divided into 2 zones. The zone of saturation, where the pores or openings begin solid particles are filled with water, and the zone of aeration, where the pores are partly filled with air and partly filled with water. Water infiltrates down under the influence of gravity until it meets the interference between the zone of saturation and the zone of aeration, right here. This intersurface is called the water table. The depth of the water table below the surface varies with the amount of infiltration. The subsurface water below the water table is called groundwater. It is groundwater through wells that supplies a large portion of human water requirements. Withdrawing water from wells faster than it can be replenished lowers the water table. Porosity, the percentage of open space, pores, and cracks in a material compared to its total volume, is porosity. Generally, the greater the porosity of the loose materials at the Earth's surface and the rocks, the greater amount of infiltration that can occur. The shape, packing, and sorting of these particles composing a material determine its porosity. Shape Well-rounded particles have greater porosity than angular or plate-shaped particles, because round shapes do not fit together as tightly as other shapes do. Packing. The more closely packed the particles, the lower the porosity. The constant passage of people, animals, or vehicles in the same place or path will pack the soil, lowering the rate of infiltration. Sorting. If all particles in a material are about the same size, they are said to be sorted. If the particles are of mixed sizes, they are said to be unsorted. The more unsorted the particles, the lower the porosity, because the smaller particles can fit into the spaces between the larger particles. It should be noted that the particle size by itself does not affect porosity. For example, a material with larger particles may have about the same porosity as one with smaller particles if the shaping, packing, and sorting of both particle sizes are about equal. If there were two rooms of equal size, one filled with marbles and the other filled with basketballs, the total volume of pore space would be about the same for both rooms. Vegetation. The amount and type of vegetation in an area influences the amount of water that infiltrates the ground. Grasses, trees, and other plant types intercept falling precipitation, reducing its velocity and temporarily storing some of the water above Earth's surface. The reduced speed of precipitation gives the ground more time to absorb the water. Plant litter, dead and partly decayed vegetation, serves the same function. Some of the water stored on vegetation and plant litter falls to the ground after precipitation has stopped, and this can increase infiltration and reduce runoff. Groundwater without vegetation usually has high runoff and low infiltration rates. Land use. How land is used by people can greatly influence the amount of water seeping into the ground. Roads, parking lots, and buildings cover otherwise permeable ground and create impermeable surfaces. These impermeable surfaces can channel runoff directly into streams or drainage pipes, reducing the chance of water seeping into the ground. Farming, cutting down trees, and grazing of domesticated animals often either reduce the amount of plant life in an area or compact soil, making it less permeable. There are factors affecting runoff and stream discharge as below. Surface runoff can occur when the rate of precipitation exceeds the permeable rate or infiltration rate of Earth's solid surface. The pore space of loose material or rock is saturated with water. The slope of the surface is too great to allow infiltration to occur. And the water on the surface has not yet evaporated or sublimated to gas. Most runoff gets to streams, which often carry back the water to oceans, contemplating a major part of the water cycle. The greater the runoff, the greater the amount of stream discharge in local streams. There is a time lag between the times of highest precipitation and greatest stream runoff due to the time it takes to take water to get into these streams. Stream discharge is the volume of water flowing past a certain spot in a stream in a specific amount of time, and is expressed in units such as cubic meter seconds, or liters per minute. So here's our stream discharge and our stream velocity. Another factor affecting runoff and stream discharge is flooding. Flooding occurs when a stream overflows its normal channel. Flooding also happens when precipitation exceeds the ability of ground to infiltrate the water, and evapotranspiration is not rapid enough, and when water is not able to move to the streams quickly enough. Flooding can also be the result of a hurricane storm surge, coastal storms, and the rising of sea levels, sinking land, or tides moving water onto the land. The first rule of safety in dealing with a flood or the possibility of a flood is to move to higher ground. Accurate predictions and measurements of snow or rain might give people sufficient time to evacuate an area before the flooding. Many communities have planned escape routes determined through the study of topographical maps and other elevation models. Can you think of a flood? Now our water cycle is complete. We have our complete cycle. Replay the video if you like. And remember to click to start today's assignment.